Algodoo is a physics simulation software that allows users to create and interact with virtual experiments in a playful and educationally rich environment. It combines intuitive drawing tools with real-world physics principles, enabling users to visually explore mechanics, fluid dynamics, and more. Why are virtual experiments so compelling? Conducting a physics experiment in a simulated environment like Algodoo and then fitting it to a mathematical model is a great way to understand and validate principles of physics. Virtual experiments offer unparalleled flexibility, allowing us to replicate, modify, and control scenarios that might be challenging in a traditional lab. They hone our skills not just in experimental setup, but deepen our grasp on the intricate theoretical backgrounds underpinning each scenario. Our journey with Algodoo, for example, begins with a simple rectangular body dropping and sliding, unraveling layers of knowledge about gravitational potential energy, kinetic energy, and friction. But as students explore the topic deeper, they will be equipped with the tools to fit raw data into mathematical models, validate these models, and then critically compare them to established physical laws. Beyond the rectangular drop, we will oscillate with virtual pendulums, consider the fluid dynamics of digital liquids, and trace the arcs of simulated celestial orbits. Each module offers a chance to not only understand the what and how of phenomena, but also the why. By the end of the course, students will see that these virtual experiments are more than just simulations. They are gateways to a deeper understanding of the universe and the physics that shapes it. Here's a general approach to students' virtual experiment. Experimental setup. Use Algodoo to set up a rectangular body and let it fall from a certain height onto a flat surface at an angle. Ensure the environment settings in Algodoo, e.g., air resistance, gravity, are consistent and known. This will be critical for the modeling phase. Record the data points you are interested in. For instance, you might measure the time it takes for the body to come to a stop after impact or the distance it traveled. Theoretical background. Before fitting the data, it helps to have some understanding of the underlying physics. For a falling object, you'll be primarily dealing with gravitational potential energy, kinetic energy, and friction. The gravitational potential energy is U equals m times g times h, where m is mass, g is the acceleration due to gravity, and h is the height. This energy gets converted to kinetic energy during the fall, and subsequently, some of it is used to move the object on the surface, and the rest is lost due to factors like friction. Data fitting and model creation. Once you have the experimental data, you can fit it to the theoretical model. For the motion on the flat surface after impact, consider the model. F friction equals mu times n, where m is the coefficient of friction and n is the normal force, usually m times g for a flat surface. This frictional force will decelerate the object, leading to the equation F equals m times a, which can be used to model the deceleration and stopping distance. Depending on the complexities involved, Hoji, if there are losses during impact, non-uniform friction, etc., you might need a more intricate model. Use a tool like MATLAB, Python, with libraries such as NumPy and Scipy, or even Excel and Origin to fit your experimental data to the theoretical equations. Validation. Once you have a model, predict outcomes for different initial conditions and then test these in Algodoo. If the predictions closely match the simulated results, you've validated your model.